So let me conclude this workshop with the last presentation, that is the digital twins for the hyperdistributed 6G edge network. That basically is the research that we have been doing at UC3M regarding digital twins and how we see that the digital twins of the future can be applied to the manufacturing world. Okay. So basically, in this area, what we were looking at is, okay, we want to have a factory, what would they call factory of the future or industry 5.0 even, that is a flexible factory where we have robots that are connected through a wireless connection to the factory floor, and we have digital twins of everything, and we can reconfigure the different robots and so on. In order to do that, we wanted to look at the different concepts that we have deployed in HDT. That basically is to have computing in the manufacturing plant, okay, located everywhere, and that we can basically move the computation needs and the software that is running right now in the robots into this computing fabric that is spread in the manufacturing plant. So in this presentation, I'm going to focus on these two main contributions. The first one is basically, why do we need 5G or 6G in order to do this? Okay, so basically, what are the connectivity choices that we have, and how can we take benefit of this new low latency communication in order to have something new that before was not done regarding the cloud robotics, as we call them. And then, how can we use digital twins and artificial intelligence in order to improve the operation of these digital twins that we have created in the first part? So looking into this, let's focus in the first part, that is the connectivity technologies that are key in order to develop this connectivity scenario. And here we were looking at three main challenges. Basically, these challenges focus on how do we achieve this vision of the factory floor that is reconfigurable and is full wireless. Okay, so the first thing is how can we bring wireless into these robots? How can we take benefit of the wireless domain, and what are the things that we can do in wireless that we cannot do in wired technologies? Now, how can we achieve the real-time connection synchronization, and what is the penalty of paying in terms of energy of using the wireless communication for this scenario? And basically, how can we unify all of this in one digital twin of a robot that works wirelessly into the factory and can be controlled using a wireless connection, in this case 5G. Then what we have done during this research basically is we have first investigate how to do this using the connectivity technologies that we have, what is the best option for the factory. Then we have designed and implemented an edge robotic digital twin, where we have basically a digital replica of a robot that is synchronized perfectly via wireless domain with a robotic arm, and that we are able to operate remotely. And finally, we have evaluated the performance in order to understand where are we and what can we achieve. So considering this, what have we developed? Well, the first thing that we did when developing this idea was we based our idea of edge robotics into the concept of functional split in 5G, which is a little bit weird. The functional split in 5G basically is how do we get a radio head, okay, well, a GMB, a radio base station, and divide it in things that are compute in a centralized location and things that are distributed in the different antennas. This concept was applied into the robot. How do we do it? Basically, we got the robot and we were analyzing the different software stack that was running in the robot, and we were measuring if we could move portions of this robotic stack into a centralized cloud server, okay, so cloud server or edge server. In order to do that, basically what we did is we got the ROS protocol stack. We divide each of the functions in a Docker, in this case, okay, in a container, and we were checking if we could move all of that into an edge server that is in the core, okay? In the core, of course, we are talking a local core, okay, in the factory floor. In order to do this, what we did is, as explained in this figure, we took every part of the ROS modules, we Dockerized it, we place everything in an edge server connected to a 5G NSA, connected to a radio, connected to the robot, And these are the different specifications that we use. Basically, for CP, we use a Huawei one. We have an NSA network provided by Ericsson in Phitonic. And then in the robot, basically, what we were able to achieve is to take out all the control part of the robot, move it to the edge, and in the robot, just leave the drivers. So basically, we have a completely stupid robot in the factory that can be reprogrammed in a central location, changing whatever is needed very quickly in one place, coordinating a lot of different robots. And then we run that, and our robots do whatever we want. And we have, on top of this, a digital twin that is this web here, okay? It's digital twin connected to a web that is controlled remotely. So we have an operator that is able to do the movements that it wants in a digital twin, and this movement is replicated in real time in the factory floor. So, and finally, as digital twin, we use the Coppelia Sim 3D program, okay? And the Nirio one is our robot. Right now, we have developed this, and we have an evolution using a robot dog that is very nice, but it's not in this slide set, okay? So first thing first, can we do this? Are we able to move all the intelligence of the robot to the edge and to control it without a loss of performance? The answer is yes, okay? So basically what we did is, this is the flow of functions that, that any movement of the robot has to do. So basically, the digital twin, we tell the interface, okay, I want to do this movement. The interface will talk to the motion planning. Is this movement possible? If yes, the motion planner will give you the set of coordinates that you have to execute. Then the motion planning will tell the robot to the joint states, move. The sensors will detect the movement and will come back. And we will have a feedback loop, okay, in order to do that. Here, the first thing that we did is to measure the different times required in order to do this. You can see that for some operations, it's almost half a second, okay? So we have plenty of delay budget in order to work with. And basically, the green line here is when we put the control, we put everything but the drivers into the edge, and the black line is when everything is in the robot. They have a small delay, of course, you have to move the information to the server, but they are perfectly synchronized. So this is doable. We can move all the intelligence of a robot into an edge and operate it without any loss of performance. Okay? Second question. Do we win or save something while doing that? CPU and memory, energy consumption, transmission and reception of data. In the first part, CPU and memory, if you analyze which parts of the drivers control motion and interfaces is taking the load, okay, you can see that basically the drivers are constant across all the different instances. So basically, here we have everything in the robot, here we have everything but the interface in the robot, here we have drivers and control in the robot, and here only the drivers, okay? So we can move a lot of computing power and memory and save a lot of resources if we move this from the robot to an edge server. And this will help us saving money. Why? Because the robots will be less expensive. They don't need a powerful CPU, okay? In terms of energy consumption, doing the same exercise, basically we can see that if everything is placed in the robot will consume a lot more than if not, okay? So we are saving energy doing this by concentrating everything in an edge server that in fact is prepared for this kind of workload, so it can be more efficient than having everything in the robots. And of course, in terms of transmission and reception, so data, of course, if we place everything in the data center and we are controlling remotely the robot, we have more. Okay, we have more transmission and reception. But the key thing here is that this part is pretty efficient. We have done our job in 5G and other technologies, and transmitting and receiving data is something that we do very well and very efficiently. So we don't save much in terms of data if we place everything in the robot. Now, and this is a very interesting slide. We know that via a wire, we can move everything to the edge, and it works without loss of performance. We know that we can save money if we move all the control to a server, okay, because the robots will be cheaper. We know that we can save energy. because the centralization of everything will consume in just one server, but each robot will consume less. The question is, which kind of technology can we use in order to do that? Because not all technologies are going to be able to support this data rate and this delay. And what we did is an analysis of Wi-Fi, 4G, and 5G NSA. In this case, the robot that we were using has a control loop of 20 milliseconds. This means that every 20 milliseconds we are receiving a command. And if you don't receive anything in 20 milliseconds, the robot will stop. Okay? Then you will need to wait for another 20 milliseconds in order to recover. So considering that, these 20 milliseconds, we can see that for 25, 30, 35, and 40, basically 4G will work, 5G of course work, Wi-Fi works, but for 20, 4G doesn't work, okay? So for 20 milliseconds control loop, in 4G we cannot do this. We'll lose synchronicity and the robot doesn't operate as it should, okay? So basically we need 5G, we will need 6G, we will need Wi-Fi even 7 in order to run this. Why I'm saying this? Because 20 milliseconds is a research robot, not an industrial one. Industrial ones now can be 1 millisecond, closed loop. 1 millisecond, this will not be enough. So we will need 6G in order to operate this in a factory with the last version of the robot, okay, the newest one. So with this, I conclude the first part of this presentation. And now let's have a look on how can we integrate this with artificial intelligence, okay? And what are the benefits of doing so? So what we are trying to achieve here is basically we discovered that in this case, well, let me tell you the story of this. We were testing this robotic arm with Wi-Fi in a laboratory where we don't have any interference. And everything was wonderful. We had this graph, everything worked like a charm, perfect. We moved the robot to another lab where there is more people, there is more interference, and the robot broke. At some point of time, the robot in one of the movements started operating really like in a small jumps, and at some point of time, one of the joints broke. Why? Because we had in the lab next door another guy doing an experiment in Wi-Fi and was jamming completely the spectrum. So the packets were getting lost, and from time to time, we were getting another one telling you to move very fast to the other side of the room. So the robot was doing like this, and the joint was broken, okay? So we decided that, okay, this is something that for sure we can remedy forecasting what is the next command. And this is where all this work pop up, okay? We were starting looking at, okay, if we have AI and we know what are the different movements that we can do, maybe we can forecast what is the most probable command that you should receive. And in case there is a failure in the channel, you use that, okay? So that's the motivation. So what we did is we propose a machine learning-based command forecasting. We automate the dataset generation through digital twinning. We will go into that in a moment. And basically, we have a running prototype of this, okay? So first thing, dataset collection. One of the very nice things of having a digital twin is that you can use it in order to generate a lot of samples and train AI ML models. As I have shown you in the first part of this presentation, we have a digital twin. We have a digital replica of our robotic arm. So what we did is program this digital replica, replicate it a lot of times, this digital twin. So we have something like 100 robots moving asynchronously, and we collected all these samples in a huge data set, okay? So basically, we had all possible movements of the robot for the pick and place task that we wanted. With that, we train an AI model in order to do this, okay? As you can see, we have quite a lot of commands. We have different parts for validation and inference and training, and so on. So the typical model, okay? With that, we train a model that we call ForEco, that is forecasting, where we have these results. Basically, here we have the trajectory that one of the axes of the robot should take when doing a pick and place, okay? So you go up and then you go down. The red points are when we have a jamming into the channel. So there are no commands arriving at the robot. So basically, the robot doesn't know what to do. At some point of time, you recover because the jump has finished, and then you have to move very quickly to another position, okay? And then it slowly recovers and go to the defined trajectory. And then we have for echo, our forecasting, okay? And as you can see, of course, there is a small delay, okay, a shift in the operation, but it resembles a lot the defined trajectory that we wanted to have in the robot, okay? So basically, if you see the operation of the robot, without for echo, the robot is really moving with small jumps, okay? And with for echo, it's very much smooth, although of course there is room for improvement. So with this slide, I conclude this presentation. Here, what we have is the two items that we have been working on in HDT. The first one is basically how can we offload the robotic functions into an edge server and what are the benefits of that. And basically, we have proved that we can save CPU, save memory, and we can coordinate a large group of robots in one central position. And we have also proved that for 20 milliseconds, 5G is enough, but for going below that, we will need much more technology, basically. We will need 6G for this, okay? And then we have also seen how we can have AI/ML in order to improve the operation of this kind of processes, and how a digital twin can be used to very quickly and very efficient training of this machine learning model. So thank you very much. Some references.
Have you evaluated the impact of the AI in the robot?
What do you mean?
When you deploy the inference in the robot, that will have an energy impact there.
We didn't, but it's running in a Raspberry Pi, so it doesn't cost very much. Tell me.
Do you see any security using the AI in the robot? Yeah, you want to make sure that the robot doesn't destroy.
Yes and no. I mean, I agree with you that this is something that we have to look closely, okay? But as the use case is a remote operation of the robot. So even if you don't have AI, we will need these issues. So I don't think AI is adding anything more to the mix, okay? But I agree, probably there is something we need to look closely. Another thing that we were looking at is how can we add to this digital twin model cameras in order to understand what is the vicinity of the robot, okay, and maybe stop if there is some human nearby or something like that.
Maybe to follow up on this question, what kind of cameras do you have? Or is this the next step?
This is the next step. Said so, we were looking, we have one camera that is similar to the Kinect from Xbox, similar to, it's not the same one, that has depth. I can give you the reference somehow. Thank you. Someone else?